Um, at JPL, we manage the AIRS instrument, which is in the lower left corner. It's a facility class Earth observing system instrument. It's a big gadget. It's a 100 million plus, actually is more like $200 million instrument on a $1 billion spacecraft. And so, but it's working great. This thing's been up there 15 years, but we're also looking at how to do this smaller and cheaper and provide better timeliness, because this is just one satellite. So let's go to the next slide. The AIRS measures the spectrum of the atmosphere from about 3.5 to 15.4 microns. We're measuring CO2 absorption for temperature, and we measure the water vapor absorption lines for water vapor. So it's a temperature and water vapor sounder. The idea being this thing will help weather prediction and climate forecast. So next slide. So these sensors have provided the highest impact of any single sensor type next to the microwave. And so the infrared and the microwave are sort of the mainstay for weather forecasting. Well, they're developing the CRIS instrument, which is they have them lined up all the way into the 2030s. But we expect these little CubeSats to be able to improve the timeliness, and I'll explain a little bit more about what it can do. But it should be complementing the current system, not necessarily replacing it. So JPL is developing we're sort of the lead on the thing. We're developing 3 technologies to demonstrate. One is a hot bird detector. It's a new detector to replace Mercad, an immersion grating, and black silicon black body. The whole thing will be packaged up as a spectrometer in a 6U CubeSat in a morning orbit. We only really need to last 3 months to demonstrate this technology. We'd like to get about 100 hours of science data operations. Currently, BCT is saying the instrument can remain on, but in terms of pointing at the Earth, because of our power arrangement, we expect to be charging for 2 orbits and acquiring data for 1 orbit. And of that 1 orbit, we don't even need the full orbit. We just need a few granules in that orbit of data, so that we don't expect there to be a lot of data for this particular demo. But in the future, when the subsequent units that NOAA would have to be 100% duty cycle, and have much better reliability, so they could last for a couple years. And it's a totally different paradigm there. But this project is a tech demo sponsored by ESTO as part of the Invest. We're working with NOAA on this. We expect to be completed in May of 2018 and launch September of 2018. That's with the spacecraft. The payload's in May. The spacecraft with the payload and everything's done in September of 2018, and we launch no earlier than January 2019. Okay, next slide. So the idea is this system projects a slit on the ground. It scans. We have a scan mirror on here, and we use the focal plane array to build up pixels, spatial pixels, and the scan motion to build up spatial pixels in the other direction. And then we preserve the spectral direction, which is horizontal in the figure, for the spectrum. So we have 625 frequencies we expect from this thing. So this is going to be a demonstration of a science class instrument. And then because we can bin up the pixels, we can go into a zoom mode and do sounding in more critical regions and improve our yield. Okay, next slide. So this just shows the spectrum of the atmosphere in orange there, and overlaid on it in purple is our spectral resolution. We have better spectral resolution to the left, which is in the water band. And to the right there, you see the CO2 absorption feature. We use that for temperature, and studies have shown that this particular band should be good enough for doing temperature and water vapor. We have a problem of reflected solar, and that's something the scientists are going to be looking at. But other than that, things should be very fine. Very well. So next slide, please. So this is a cartoon, an earlier one we have of the instrument with some updated figures of the modules inside, and it's a 6U CubeSat. And on the left side there, you'll see the spectrometer. On the bottom, you'll see a scanner with the little black body target. That's our black silicon. We've got a scan motor in there that operates the scan mirror, and we have two cryo coolers on here. So this thing's a power hog. This is an old figure, but we were somewhere around 37.5 watts at the time. I think we've come down considerably from that. But we have two coolers, and then on the right side you could see the spacecraft avionics there. And a lot of this technology is commercially available, but we're developing the spectrometer and the detectors and all that custom for this job. Okay, next slide. So this is just sort of an evolution of the technologies, but we can go to the next slide. And then these are the status of the current technologies. So as of today, or as of last week, I should say, maybe a couple of weeks ago now, time's flying, we've completed building our detectors. This little thing in the upper right is an image from one of our focal planes. These hotbirds are amazing. They have exceptional uniformity, exceptional operability, and performance is good. I wouldn't say it's great. I've got a quantum efficiency of about 35 to 40%. The dark current is about the same as Mercab, but you can operate at a little lower temperature because all the detectors are the same, have very similar uniformity. So you don't have to cool it extra for those outliers. Spectrometers under development by Ball. They've built these before. These are wide field IR, high spectral resolution spectrometers. The black silicon is cool stuff we make here at JPL by etching silicon, and it's as black as the carbon nanotubes. And this will be the first time we fly it and test it as a black body. So that'll be real exciting. Next slide. So here's where we are today. I think I mentioned the detectors, but here's some of the other areas. We had our system requirements review. We're going to have a PDR CDR in September. All our contracts are in place. Everybody's working on it, and we're trying to build it. This little figure in the lower right was an animation of our scan motor at the scan rate. It's a very slow scan. It takes like 23 seconds to do a complete revolution. Spacecraft is by BCT. We started our contract with them. They could tell you more if we have time here. And let's go to the next slide. So for the future for this thing, again, I mentioned NOAA has an interest in this. We at NASA have an interest to improve timeliness of sounding measurements and measure the diurnal cycle of sounding of atmospheric processes. We also have an idea to use this for 3D atmospheric motion vapor winds. This is a very important measurement that is not being made today that the Weather Service thinks is needed. And we think if we fly 3 of these Cirrus instruments, maybe with a little longer life to them, maybe a better cryo cooler on here, we will be able to measure 3D winds because we measure the water vapor in 3D and we could track water vapor features like they're doing now on MODIS and GOES, but we can do it in 3D. And then we also have a carbon monoxide band in here, and this system should be good for measuring carbon monoxide. So the next slide. We're funded under the INVEST project. We're expected to fly in the 2019 timeframe. All our procurements are in place. Blue Canyon's going to do our spacecraft. And so basically, we're handing a lot of the mission operations over to Blue Canyon. We will define command procedures for the payload, turning it on, and some sequences for pointing the mirror and scanning and stuff like that. All the binning will be done on board on the spacecraft by software written by Blue Canyon. We'll define the algorithms for that. And let's see. At this time, we've not asked them for a Globalstar radio. We're a very cost-constrained project, and we wanted to see what we can do to get the cost as low as possible. And we're also constrained on the payload volume considerably. So I guess that's about it. That's where we're at today. Any questions? Hello?
Yes. Oh, can you hit
okay,
that?
There we go.
Thank you. Just to do you have any requirements for daily command and control? And secondly, I'm interested in your black silicon. Is this the process with which the silicon is bathed in auric acid, if I recall, to create these micropores that turn it black?
You know, I really don't know. I only know is that it's etched, and I can find out though. If you send me an email, I can find out how it's done. But as far as daily,
sorry, no, I know. Sorry. I just.
It's interesting, but this is the comms stuff.
Well, yeah. So that's why my first question was my first question was a comms.
Yeah, you snuck it in there. Yeah, well done.
Good question. You know, I envision, and for the tech demo, we're going to do as little as possible, but I do envision there being some kind of a daily commanding for this thing, even for the tech demo. We want to experiment with the different acquisition modes of this thing. It's got a lot of capability to try different things and pointing and binning and all that. So there could be, although we got to work that out with Blue Canyon and how much they can afford to do.